Is it chapter 8 homework? Okay. Let's take a quick look. Remember which one?
It was 6 part B.
Okay. This one? Alright, so got a vehicle collision here. This is going to be an maybe a mixed type of collision, but thankfully you already know one of the vehicle's final velocities, so that simplifies things a little bit. Part A is finding the final velocity of the moving van, and you need to get part A right to be able to get part B right. So, namely just for the crowd. That's the wrong marker. This is I would use conservation of momentum. So momentum car initial plus momentum truck initial equals momentum car final plus momentum truck final. And you can use that to determine the final speed the truck would be moving at, given that you know everything's mass and everything else's velocities at every other point in time. Did you get A?
Mm-hmm.
All right, so with part A done and you know the truck's final speed, you then need to find the kinetic energy of both vehicles before and after, and subtract the after total from the before total. Because this collision, I would say, is mostly inelastic. They're going to lose some amount of kinetic energy, and when it says how much mechanical energy, it is really asking kinetic. Because in physics, mechanical is more a category of energy, and kinetic is one of those types. So since the vehicles are going to lose kinetic energy, it's asking what is the kinetic energy difference from start to finish.
So is it kinetic final minus kinetic initial?
Right, but it's I would say it's the sum of the both of them. So KE car initial plus KE truck initial minus the sum of KE car final plus KE truck final. Because it wants to know from before to after how much energy isn't kinetic energy anymore, because now it's just heat in the road. What else feeling? Anything else on your minds before we get started? All right. It is. I finally have a marker sorting system. All the dead and dying ones go here, because they don't have a trash can. These are my good ones. Does that help for now?
Mm-hmm.
Okay. We can come back to this later if you'd like. Main thing for this week is we have one last short chapter before we enter test territory. Chapter 9 is going to be about pressure and buoyancy. I just realized this morning that my numbering on Brightspace was off slightly, so I've reworked that a little bit. Chapter 9 is about pressure and buoyancy, and I've added the notes that I'm showing today to that. If you don't have them yet, they're there now. And the main thing I want to do today is begin this chapter, and I'm going to kind of be changing tactics a little bit. I want to kind of look at the bulk of the formulas from the chapter all in one day, so that you've seen all the formulas, and then practice them Wednesday and in lab. So today is introductions and learning about the formulas. Wednesday in lab is going to be understanding them and building context. Does that sound fair? Okay. Please let me know if you have any questions or objections at any point in time. Once again, this chapter will be about pressure and buoyant force. Now, I'm under the continued assumption that most of my students are either chem majors or bio majors, which means they still have to take an amount of chem classes anyway. So I assume most of you are familiar with pressure used in scientific contexts, say like in PV equals nRT. Not familiar, I hope. All right, so the pressure we're talking about here is the same pressure, but it's going to extend beyond just pressure involved in a chemical reaction. We're going to be looking at both that and also pressure as a whole, but also how pressure creates the phenomenon known as buoyant force. That's just floating. It's the force that causes floating. Same root word as buoy, because if you're floating, you are buoying on the surface. Now, we're going to focus primarily on pressure that fluids create on solids. So, real quick, I want to make sure that it's in your head that fluid can mean either liquid or gas, or technically plasma. It is a fluid, just don't ever be submerged in it because that will hurt. But technically, liquid, gas, and plasma are all fluids. They all exhibit fluid tendencies, which is to say they have an indefinite shape. They can actually deform and allow something to be submerged in them, unlike solids, which have definite shape and don't yield very easily. Gases and plasmas also have indefinite volume, but we're going to focus mostly on indefinite shape and the ability to submerge something within a fluid. So fluid, mostly we're referring to both liquid and gas. Fun fact, that technically means plasma. Further fun fact, there's a fifth state of matter, but you'll never encounter it. It's called Bose-Einstein condensate. It's functionally anti-plasma. Instead of plasma, plasma is common and hot. Bose-Einstein condensate is so rare you'll never find it, and cold. Which is to say it exists at absolute zero, which doesn't happen. So, in terms of pressure, again, we're going to focus primarily on how pressure acts on solids and how it is created by fluids. And again, fluid, I'm going to refer both to liquid and gas. Technically, you are submerged in fluid right now. This will become relevant later. As I said, we're going to run through a lot of formulas and vocab words today, just kind of laying the groundwork for the rest of the week. First off, let's review density, which as a concept I know you use regularly, but just so it's in your notes. Density is mass over volume, how much material is in a unit volume. In this class, we like to use kilograms per meter cubed for density, because we like kilograms and we like meters. Liters will come up occasionally, just because graduated cylinders have milliliters written on them. When that happens, I'll make sure the conversions between liters, milliliters, and meters cubed are all written and available to you. Confusingly, the symbol for density in physics is still rho, which is the same symbol as momentum, unfortunately, because as I said, physics ran out of alphabets to steal from a long time ago. But I will try to make it clear in any formula, whether it's rho momentum or rho density. Thankfully, the two concepts have nothing to do with each other, so you shouldn't have to mix them, at least in this class. Main thing that I want to focus on for this particular moment is the pressure formula. This is the definition of pressure, and that's again what these three lines mean. Definition of density is mass per volume. Definition of pressure is force over area. When you feel pressure, that means that there is a force acting over the surface area where that pressure is being applied. Within, say, chemistry context, if you've got a gas inside of a container that is exerting pressure on that container, that means the gas is exerting a force across the container's internal surface area. But that's not just true of gases inside of containers. It's also true of gases outside of containers. And you are a container, meaning that the atmospheric pressure around you is exerting force on your surface area. Humans aren't a standard geometric shape, but we do have a flat surface area, and the air is literally pressing in on that area at all times. We like newtons for force and meters squared for area. So that means this formula would give you newtons per meter squared, and we call that unit a Pascal. Do you guys use Pascals on the chemistry floor? Okay, cool. 101,325 pascals is standard atmospheric pressure, which if you use them regularly should be in several of your notebooks, but again, conversions, I will never hide them from you. So this is currently the air pressure that you are under right now, barring variances in elevation and temperature. And once again, that pressure is exerting force on the surface area of your body. Pressure is capital P, not to be confused with sometimes in a formula sheet you might find uses capital P for momentum. Sorry, again, we ran out of letters. I like capital P for momentum, for pressure, and rho for momentum, but that still conflicts with density, so whoever's writing the notes, there's always going to be a problem. But again, momentum shouldn't mix with either of these concepts, so I'll make it, if you need to ask me, I'll clarify. So, quick general review of the pressure definition. If you double the force that something exerts on something else, what does that do to the pressure it exerts on that object? Double the force, area stays the same, double the pressure. So, in your chem experiments, whenever gas pressure doubles, that means it's literally exerting twice the force on its container. Other side of that, let's say we keep the force the same, but we cut surface area down by half. So surface area is now half as big. What happens to pressure? Not quite, because notice that A is in the denominator of this side. So say what we were doing before is 1 over 1 equals 1. 1 over 1/2 is 2. If you keep the force the same, but reduce the surface area it's applied over, the pressure gets bigger. I find this interesting from like a human sensory perspective. Because as it turns out, your nervous system, your skin nerves, can't really detect force. They detect pressure. Because every force you've ever felt, barring gravity, which doesn't, every contact force you've ever felt that requires physical touch, has been over a surface area. Like if you touch something with your hand has a flat area to it. Again, it's not a normal geometric shape, but it does have one. You can find the surface area of the palm, and all the forces you exert through your palm are divided over that area. So every force you've ever felt has been over an area, and that means what your nerves detect is pressure, and high pressure is what causes pain to human skin, and also causes pain to humans. The force itself, surprisingly, doesn't matter all that much. For instance, say you take your entire palm and lean up against a wall. The force I'm exerting is distributed over the whole palm, and that doesn't really hurt. This doesn't really cause any pain to me. But let's say instead of my palm, I put my the flat of my fist against the wall. That's at least half the surface area, if you look at this rectangle of my knuckles. And this is getting uncomfortable. It's the same force, because it's still holding me up just fine. The force didn't change, but the area is reduced. Therefore, the pressure I'm feeling is increased, and it hurts more. And it would hurt even more if I tried to do it with one finger. I'm not even going to attempt that. But this area is, like at least 1/20th that of my flat knuckles, just the tip of your finger. So that would drive, okay, I'll kind of try it. Nope, I quit. That's really uncomfortable. Again, same force, much smaller surface area, bigger pressure, more pain. And this is why throughout human history, most of our weapons have sharp edges. Because if you sharpen it, you are reducing the surface area of contact. Swords and axes and arrowheads, they all, and like in modern contexts, needles at the doctor's office. Small surface area, average amount of force, insane pressure, causes pain, breaks the skin. Makes sense so far? All right, one more context building endeavor. Again, this is atmospheric air pressure right now, because 1 Pascal is teeny tiny, so it takes a lot of them to equal 1 atmosphere. 1 Pascal is 1 Newton per meter squared, so 1 Newton isn't a lot, and 1 meter squared is a big area, so we got Pascals of barely nothing, barely anything. But if we assume that a human has an external surface area of about 2 meters cubed, how much air force would the atmosphere be exerting on that person's body? Pressure here is air pressure. Force is unknown. Area of the human in question is 2 meters cubed. And so, Earth's atmosphere would exert just over 200,000 newtons of force on that person's body. And that's about my surface area. So right now, the atmosphere itself is crushing me with 200,000 newtons of force, which is 200 times what I weigh. And I don't feel it. But, this is happening to you right now. The weight of the atmosphere is literally crushing you, and your nervous system is designed to ignore it, which is good, because if you could feel that, it would drive you crazy. But do you know why? Well, I already said, your nervous system is designed to ignore it. But even more interestingly, in my opinion, your body needs it to live. The atmosphere is a weighted blanket that we cannot survive without, besides the fact we need to breathe it. The interesting thing about pressure, it works a lot like normal force. The force is always perpendicular to the area it is acting on. So atmospheric pressure pushes straight down on the ground, but it actually presses inward on the side of buildings. And humans have very, again, geometrically speaking, non-standard shapes. So this force is pressing in all directions at all times on us, inwards on every surface. So a second reason you don't notice it is it's not all pointing in one direction, it's cumulatively inwards, so it kind of cancels out a little bit. Like the rightward force cancels the leftward force, the downward force is mostly negated by the upward force. No, reverse that. So that's another reason you don't notice it. It's inward and canceling out most of the problem. But you don't really notice it crushing you, because again, your body needs it. You're designed to have that present, which is why if you go to space, where you don't have that, you die. This is why, at least in movies, depending on what movies you've seen, some people explode in the vacuum of space. Our bodies are designed to be crushed by this at all times. So your own blood system is exerting a force out to negate it. And that doesn't turn off. If you go to space, that doesn't shut off. So if you're in the vacuum and this inward force is just gone, your body doesn't know to turn off the outward force, and you literally rip yourself apart. Which is, bad. So, we are being crushed by the atmosphere at all times, and we love it. Questions for just any of this context building? All right. Now, Earth has air pressure, largely because Earth has gravity. So, not scale drawing. The atmosphere is just a gas bubble that's being held in place by Earth's gravitational pull, and this tends to be why planets with weaker gravity don't have atmospheres. The Moon has no atmosphere. Mars has less atmosphere than Earth. And the pressure that we are currently dealing with from Earth's atmosphere depends not only on the strength of Earth's gravity, but also the density of the air and how much of it there is, namely how much of it is above you. So, second formula for pressure for the day. This is the pressure that a fluid exerts on you when you are submerged in it. And again, gases are fluids, so you are submerged in a fluid right now. There's a certain height of specific density air above your head. Gravity is pulling down on that column of air, and the weight of that air is what creates the air pressure crushing you right now. So, again, pressure from fluid equals density of the fluid. So if it's air, that would be air's density, which is not much. G is 9.8, and again, this is one of those cases where we care about the strength of the gravity, but not the negative sign. And H is height of fluid above the spot you're measuring. So if we were looking at air pressure, it would be the height of atmosphere above your head. This is the reason why your ears pop when you elevate. Because if you're up here instead of down here, there's less air above you, therefore there's less air pressure, and your ears are the part of your body that is most sensitive to pressure, since hearing requires sensing pressure waves. And that's why your ears pop. Yes?
On the equations sheet for pressure, there's, in front of the PGH that we just talked about, there's PO. What is that?
Right. Good question. So that formula is actually for true pressure, come to think of it. What that means is, when we're on Earth's surface, we are subject to the air pressure. And if on Earth's surface you jump in a pool, there's now a column of water above your head. You can figure out how much pressure the water is adding, but the air pressure doesn't go away, because the air is pressing down on the water's surface. So what that formula is saying, the true total pressure on you is equal to normal atmospheric air pressure plus whatever additional fluid you happen to be in. So, say if you are underwater, air pressure still exists because it's pushing down on the water's surface and you can't really escape it. And then you're adding on the pressure from the water, water density, depth underwater, etc. So
we only use the equation that's on the board right there for water.
This is the general version.
Okay.
This is the general form that is just used to tell you what a specific fluid is doing by itself.
Okay.
You could use it to find atmospheric pressure at a different height, You could use it to figure out what pressure the water is adding to you when you go underwater. But if you go underwater, that does not get rid of the atmospheric air pressure. So you would, if you use this by itself to find additional water pressure, and I asked you for true pressure, you'd add atmospheric pressure to that. Thank you for asking. Does that answer the question?
Yes.
Okay. Yeah, if you were to modify your formula sheet at all, I would put a true on that first pressure and change that initial to air.
Okay.
But that is what I would say is the more general, non-specialized version of the formula that just defines depth within any single fluid. But this is why, kind of the inverse of climbing a mountain. When you go very deep underwater, you're adding water pressure on top of what you're already used to on planet or on Earth's surface. So going deeper underwater just adds more and more pressure onto you, and that's why, again, your ears will hurt in the opposite direction under the ocean. Again, this is true of any fluid. That includes the air, that includes water, that includes anything else you decide to swim in, I guess. Other planets have different gases in their atmospheres with different densities, and that affects their pressures, especially the gas giants. Questions at this particular time? All right. Tiny bit of practice just to get it into your notes. Let's say we're going to jump to the bottom of a 3-meter deep pool. That's about 10 feet. And we're going to figure out the, hold please, you made a very good point. I want to make sure that this is the, so, I mentioned again, ears are sensitive to pressure. We're going to figure out the pressure that you add by jumping to the bottom of a 10-foot deep pool and then see how it affects your ears. 3 meters underwater. And since we like kilograms per meter cubed, that would make water's density 1,000 kilograms per meter cubed. So, by jumping to the bottom of that pool, you have added 29,400 pascals of pressure to yourself. Comparing that back to normal atmospheric pressure, that is about 30% increase. Which, trust me, at least for me, is enough for me to be able to feel and start being in pain. Or at least uncomfortable. But this would normally be the case if you got your head to the bottom of a 10-foot deep pool. Now again, if I asked you for true total pressure, you would add atmospheric pressure to that. But the human body's pretty good at dealing with that pressure, so often I'm just going to ask what the additional pressure is, because it's the additional that is what's possibly causing discomfort. Because again, we tune this out. We ignore this. It's only when this changes that it becomes weird. So that's just from the water, and that means we can figure out the additional force that is acting on the surface area of your eardrum. Surface area of an eardrum is very small, about 7.85 times 10 to the negative fifth meters squared. And since we're only using I'm just going to use the water pressure here. So this is just the additional force the water is adding that you're not normally used to feeling. About 2.3 newtons, which isn't actually a lot, but note that your eardrum is very sensitive, so that would be like someone jamming a finger in your ear. And it only gets worse the deeper you go. Questions, issues, concerns? Yes?
So our blood pushes enough force to go against the atmospheric pressure,
Yep.
and that doesn't affect us like at all.
Well, it does, but note that your blood pressure is pushing out of you. Like, your blood is a fluid, it has pressure, and that means it's not only using that pressure to push forward, but also outward on the walls of your veins and arteries. I almost said one or the other. And that pressure is being mitigated by the atmospheric pressure in. So as long as both are true, you're fine.
Like us just generating that pressure by itself doesn't affect us.
No, not direct. Well, again, not a biologist, so that particular example is not my strong suit. But I know the air pressure is there, and I know your body has to be designed to account for it. I've been informed that part of the system that your body uses to account for it is your blood pressure. I assume your muscles would also have something to do with it. If anyone actually knows more about that than I do, please let me know. But yeah, the idea is your body creates its own outward pressure to negate this. And again, that's why if the two are out of balance, that's when things get weird. Because your body can't really turn this part off. If it is tied to your blood flow, you really can't turn it off. All right, last thing I want to do today, again, we're running through a bunch of formulas. We got one more I want to talk about so we can practice all this together over the week. We're going to look at buoyancy, the reason that things float. So, I find it easiest to show why this happens with a cube. So, we're going to take this cube and put it underwater. We've talked about how pressure increases with depth, correct? We've also talked about how pressure exerts force on area, namely the water is going to press inwards on this cube on all of its sides. Combination of those two things creates an interesting effect. We're going to look at the sides of this cube first. Inward on these flat sides would point, rightwards here and leftwards here. And because the pressure increases on the lower parts of the cube, even if just by a little, that means that the force actually increases on the lower parts of the cube. Oops. So there's more inward force on the lower part than the upper part. Now, on the two sides, that doesn't mean much because this arrow would negate this arrow and so on and so forth all the way down. So it's not gonna drift left or right or anything because of this. What gets interesting, in my opinion, is what happens on the top side versus the bottom side. Because the entire top is at all one depth. So the inward pointing arrows on the top wouldn't change. And neither would the inward pointing arrows on the bottom, except since the bottom is deeper than the top, the force down here would be bigger, and coincidentally, because the pressure has to push inwards, they would be bigger upward. So right now, this is all of the overall forces that the pressure is exerting on the walls of the cube. And just because of the sides canceling out and the downward force on the top technically being smaller than the upward force on the bottom, they add up to create a net buoyant force upwards. And that is why things float. Or at minimum, it's why you feel lighter in the water. If an object, namely if a solid, is submerged in a fluid, then the net force from the pressure on its area is going to point upwards, and we call that force buoyant force. Technically, the air is doing this to you, because the air is a fluid and you are submerged in it. It's just air is so thin you don't notice it doing this, really. But technically, if we didn't have an atmosphere, moving around would be, well, you'd weigh more, but you also wouldn't have to push through the air, so it might even out. So this is why things float. It's where the buoyant force comes from. And we calculate that force using something called Archimedes' principle. This has to do with that story of Archimedes submerging an object in the bathtub and figuring out how to measure its volume, noting that it displaces water when it does that. If you've heard that story, it's indirectly what we're talking about. So FB is buoyant force. This is the upward pointing force that the fluid generates. And the formula for that is buoyant force is equal to fluid density, not the density of the solid object, but the density of the fluid you are being submerged in. So if you're in water, that's the water's density, not your body's density. Fluid density times the submerged volume of the object, so that is about the solid object. And it's only about the amount of it that is under the water. If it's partially submerged, you only use the submerged part of its volume. And lastly, G, because as it turns out, buoyant force is still tied to gravity, like how just fluid pressure in general is on Earth. Now, this is because what I just said a second ago about where the buoyant force comes from is still true, but coincidentally, the strength of the buoyant force is also equal to the weight of the water displaced by the solid object. So when something is submerged in water, it pushes water out of the way because the water can't occupy the same space. That water pushes back because it wants to regain its space. The water removed has a certain weight, and the force it pushes back with is equal to its own weight. And that is again why there's a G in here. Questions about the formula itself, or we just practice it once? All right. We have a brick of unknown composition floating in water. The object has a volume of 5 meters cubed, but only half of it is under the water's surface. If we use 100 kilograms per meter cubed for the water's density, let's first find the buoyant force acting upon the cube. Since the water's generating it, that's why the water's density gets used here. But for volume, again, we want the part of the object that is under the water. So what number do we put here? 2.5, because the 5 meter cubed object is only half submerged. That means it's only pushing 2.5 meters cubed of water out of the way. I'll just write 2.5. And this is another one of those times where we care about the magnitude of gravity, but not necessarily the direction, since gravity points down, but buoyant force points up. So if it helps, you can put an absolute value bracket on your formula sheet if you'd like. Right there. So, what is the strength of the buoyant force holding this thing up? Very good. It is a force, so it's measured in newtons again. And that's a lot. It takes a lot of force to make big, heavy things float. Note, though, that if the entire object was underwater, that number would be twice as big, right? You push twice as much water out of the way. And that's why, say, at least when I was a kid at the pool, I would play a game of taking a beach ball and trying to shove the whole thing under the water, and then let go of it and watch it rocket back up. But the whole thing under the water, more volume creates more buoyant force, and since a beach ball doesn't weigh all that much, a very big buoyant force just ejects it from the water. Connected to that, what must this thing weigh? What is the weight of this cube if it is currently floating here? Flashback real quick to Newton's laws. Net force equals mass times acceleration. What forces are acting on this thing while it floats here? Yep, buoyant force up, we just, why did I write G? Buoyant force up, we just calculated that. What else? Gravity down. If you're on Earth, you can't turn that off. So that's the net force side. Is this cube accelerating if it's floating on the water's surface? No, it's not moving up or down. The waves might bob it, but it's staying pretty much in place. So two forces add up to 0. That means they must be equal and opposite. So the general rule is, if something is floating, not accelerating, its weight equals buoyant force. Unless there's some third force acting on it. If these are the only two vertical forces, they have to be balanced for it to remain in place. Sometimes there might be a third force, like, say, a kid pushing down on the beach ball to hold it under the water, in which case there's 3 forces that have to add up to 0. But if it's only the 2, buoyant force and weight cancel out. So if something floats by itself, gravity and buoyant force are currently equalized for the depth it's sitting at. If gravity is bigger than buoyant force, you sink. You sink until the water is dense enough to generate enough buoyant force to keep you at a certain depth. And that's why some detritus from boats doesn't sink all the way to the bottom. It just kind of hovers at some unknown depth depending on its own density. assuming that the water's density ever gets anywhere near that object's density. And if buoyant force is bigger than gravity, the water shoots you up until the two are equal again. Again, beach ball. So that is a general rule you can hang on to, but it's only true if these are the only two. It floats if these are the only two forces and they equal each other. Equal but opposite. So the weight must also be 24,500 newtons. We could then use that to find its mass and its density, just to compare that density back to water. So if we know the weight, the object's mass should be about 2,500 kilograms. That's about a truck. And that mass over its entire volume can tell us the density of what this thing is made of, which I'm only pointing out to prove that it is less dense than water. So the other rule for if it floats or not is it'll float if its density is smaller than the fluid it is submerged in. Yes?
Is that the weight of the entire cube or just half of it?
Entire cube. The weight of the object doesn't change regardless of how much of it is in the water, because its weight depends on its mass and the planet. The buoyant force changes, and the rule is an object will sink until enough of it is under the water to create enough buoyant force to counter its own weight. And that's why boats are usually like partially submerged, right? There is an amount of boat underwater because it physically needs an amount of it under the water to generate the buoyant force to negate the weight of the whole ship. Submarines are uniquely capable of adjusting their density to become more dense than water and sink, and less dense than water to rise. Questions? All right. Oh, yes.
Why is it in kilograms there? I thought the normal action formula was in grams.
It is not.
It's not.
Yeah, every formula in this class with mass in it wants kilograms. It's the one unit we don't put in base because physicists just decided we like kilograms. Makes all the numbers 1,000 times smaller.
Okay.
And when you're dealing with, cars and planets, smaller numbers make life easier. All right, today was a bit of a blitz through a bunch of formulas at least. Let me know if you have any questions. Wednesday we're going to go back over all this, practice it, make sure it feels right, and lab will also be utilizing the formula so you can practice there as well. Yes?
Chapter is
9. And this is the last new information before the test. So practice this on Wednesday and then move into test review. And you guys need anything right now? I'm hoping to have that revised by the end of the week. If you need anything, have a good day. Yeah.
yes, please, thank you.